Hello. For this video, I'm going to go over assignment 4. This is going to be basically the write-up in a way, but in a more visual representation, because I think for this assignment to write up the whole entire algorithm, everything is going to be a little bit complicated to write up and might be also complicated for you to read it, given the fact that I might be not always clear in the write-up. So this is definitely, I think, hopefully a better idea. So anyway, let's go ahead and begin. So suppose you have a list like this, and right now we have a bunch of elements in this array. I don't really care what they are because it's not really important. We're just going over just the steps that this would actually perform. So we'll assume we have A0, A1 up to A14, so 15 element list. So let's suppose for right now in your program, so I'm that one hardware concurrency function to get the thread count. Let's suppose right now our max number of threads that run at the same time, so max threads, let's suppose it happens to be 5, let's say, for this system. Maybe it's not going to be 5 necessarily, but maybe it's going to be 5. I'm actually going to bring this down because I want to be able to draw right below the array, so sorry about that. So I'm just going to bring this down actually. I'm just going to bring it down a little lower. Perfect. Okay, so we have this. So basically, in our algorithm, we're going to have two different functions we're going to have. So basically, we're trying to do selection sort, but we're trying to do it faster. So think of selection sort like this. The way it works is that we first go through this array, and I guess we'll find a min element. So we have to linear search to find a min in this array, and then we swap that min element we found into the very first position. And then we try doing a find min again without this first element, because the element's already in its right spot. We find a min element in the array without the first element. We find that min element and we swap it to the first position over here, index 1, sorry. And then we do the same thing but on the rest of the array. So that's what we're doing, but we want to enhance it by using threads. So you want to find the min value faster than doing this like a linear search through the entire array. So this is going to be kind of strange, but it's still maybe fun nonetheless. So the first step is we figure out what is the size of our list. So we go ahead and just put that here. So the size of the list, so size of the list, I guess this case here is going to be 15. So what we want to do is we're going to spawn, so we're going to spawn 5 threads. We don't want to spawn more than 5, obviously, right? So what's going to happen is we're going to give each thread, well, so let me see, I'm going to put this over here. Each thread will work on size 15 over 5 lists. Now, if it doesn't divide evenly, then what would happen is one thread may have to do a little bit more work potentially. So what would happen is if let's say it doesn't divide perfectly like this way, it ends up being 3. So each thread will have 3 elements. Now, it's not going to always be perfect like this, but if it's not perfect, then one thread may have to do a little bit more work potentially. That would be kind of the situation here. So one thread will have to do a little bit more work because to make up for that situation. So that's kind of unfortunate, but that would happen. So what happened in this case is, well, we're going to create 5 threads, and then the first thread, so the thread T1, is going to try to find the min element in this list. The next thread will try to find the min in that list. So what you have to do is you have to create a thread function, and basically you're going to have, well, you can probably have this vector as a global variable, because since they're going to all share that same thread, the same vector, sorry, there's no point really passing by reference, although passing by reference to a thread function is actually not allowed. Now you can pass by reference into a thread function, but it requires a few extra steps. So I would suggest just have this vector, this initial list of elements, make it a global vector. It's okay in this assignment to do that, so why not just do that? So you have thread T4 and then thread T5. So we have 5 threads. Now this 5th thread may have to do a little bit more work potentially. If there's still, like, let's say there's a little more run over, it would have to do more work potentially, but that's okay. So now we have this situation. So what's going to happen is each of these threads is going to do a linear search on their own respective small array to find the min element in each one of these. That's what's going to happen. So we do that work, and we're going to take each of these thread results, each value it comes up with as its smallest, we're going to put that partial results onto a different vector potentially. So what would happen is, let's suppose for let's say for T1, A2 is the smallest value. So you want to store this value along with what index in the array it was in. So maybe you're going to have a two-dimensional vector, or you can have vector of structs where it stores the value and the index of where that smallest element was found. So that way you know where that element is, so you have to actually swap with that first element. After that first phase, you know what element in the array you want to swap. So you want to have those stored. So what's going to happen is, at some point, T1, all the threads are going to start pushing the results onto a different vector. So this could be a two-dimensional vector, a 2D one, or it could be, you know, a vector of structs, whatever you want to call it. So we'll assume we have this vector right over here. This is not nicely drawn like the first one, because I didn't have a nice ruler in this scenario here. So T1 will push, let's say, its smallest value read so far. So T1 will push, let's say, you know, A2. That's going to be at index 2. That's the smallest one read. So this is going to be the actual value, and it's going to be the index where it was read in. And then we're going to have maybe the next thread, next vector, let's say T4 pushes next, let's say. Because say T4 finishes quicker. So then we're going to say, well, we'll say, you know, A10, index 10 was the smallest value read. Then T3 may start pushing, so maybe have A7. This looks like a 9, so sorry about that. A7 at index 7. And then let me see what else we have here. Okay, we'll say A5, index 5, and so forth. A5, index 5. And then we're going to have the last one. I think it's T5, so A13 happens to be the smallest, let's say, and it'll be at index 13. So really, each thread will do just a linear search to find, so do a regular find min. So remember after 135 how to do that. Just have each thread do a find min on each individual one. Now, here's going to be your potential, so it's kind of like a tournament basically. It's almost like, you know, in sports, we have a regular season right here. And then out of each conference or each division, let's say we have, you know, AFC East, AFC North, that's thing of football. We have like a champion from each division. And now they qualified for the playoffs. Now they got to play each other to see who wins. Kind of like, we can think of it like that. So this case, there's one problem with this though. So we're pushing values onto this vector. Let's say T1 and T2 at the same time want to push a value onto this vector. You got to be careful to make sure that you have a mutex lock during that time. So you want to have a mutex lock. So let me put this note over here. You want to have a mutex lock when a thread pushes its you know, values onto the vector. In this case, this vector right over here. Because if two threads at the same time are pushing onto this vector, that's going to cause a problem because it could overwrite the other thread's results. And then you don't have a correct answer. So that could happen. So then what happens, okay, so now we're going to have another phase. So now we're going to have different threads running. But here, how many numbers are we going to have possible? How many values? Well, since we had 5 threads, each one push is going to be 5 numbers. So we can always assume that the number of threads amount of elements will be in this vector, because let's say we had 5 threads, there's going to be 5 partial results. If we had 10 threads, then you would have 10 of these. So you can see the pattern here. So now we want to spawn half as many threads this time. Now, if you have an odd number of threads, you want to, you know, spawn maybe half plus 1, because you want to make sure you accommodate for all this. So what will happen over here? Or actually, well, anyway, let's just first do this. So what would happen now is you're going to do this kind of tournament algorithm you're going to run. So what's going to happen here is you're going to have a thread, and it's going to compare these 2 results. So this would be a separate function you're going to have. So you're going to have 2 different sort of thread functions. The first one, T1, will compare these 2, and then T2 would compare these 2, like that. And I guess maybe you could actually just spawn only half, because this last one is going to be size 1 at the end. So really, you can assume that this one will kind of win. So think of it as like the home field advantage, you know, teams. So they automatically qualify for the next round of the playoffs, I guess. Fine. So In this case over here, we compared between two adjacent values. And we're going to compare their values, which one's the smaller of the two. And the one that's smaller, that's going to be the one that wins. So what's going to happen is, well, you're going to pop the bigger one off because you want to remove. Let's say, for example, you have, let's say A2 is a smaller, let's say. Then you want to remove this one from your vector. So maybe you would do like an erase to remove it, and then, slide things down. But I think if you do an erase on this element, it would just sort of, shift it down. I actually didn't erase in mine. I just kind of always marked which one was the smaller one so far, but I suppose you would be able to, like, pop the larger value off, so then you remove those values. So what happened now is the same idea. Once we do one sort of trace of this determinant algorithm here, out of each of these adjacent ones, one of them is going to be the smaller one. So the one that's larger is eliminated from the playoffs. So what would happen now is potentially we would have, let's say A2 was a smaller and A5 was smaller. Then what's going to happen now, we're going to have fewer elements on this vector now. So what I say, A2 was smaller, so we're going to have A2 and 2, and I believe I said A5 and 5. And let's see over here, then we have A13, 13 still. So here's our new state, here's our new playoff bracket right now. So we eliminated a couple of teams. So now we're getting closer to the end. So again, we're gonna keep spawning half as many threads. So let's say we have 5 threads, we're gonna spawn 2 threads again, because now we're gonna keep on doing this, because now we have fewer number of partial winners right now. So we're gonna again do the same process, but except now, in this round, we spawned 2 threads. Now we're gonna spawn just basically sort of 1 thread, because, well, we have half as many elements, or roughly half as many elements left. So what happens here is we spawn just 1 thread only that will compare the adjacent values. So if let's say I had, let's say I had 16 threads, let's say my system could hold. Then I had 16 results over here. I would spawn 8 threads to run this simulation, and then I would spawn 4 threads next round, then 2 threads, then 1. So it's kind of like a playoff simulation in any kind of sport that you watch. If you're in esports, they probably have playoffs there too, I'm guessing. So, same idea. So we have this elimination round going on here. Same idea over here. We're going to have a thread that gets spawned, which will compare these two with each other. And then we see which one is smaller of these two wins. So we're going to eliminate the one that was worse. Let's suppose that A2 was a smaller one. I don't know, just for some reason. So we're going to have A2 left. And now, this is going to be our Super Bowl, or our championship, whatever you want to call it. Because now we have 2 teams left. 2 values left. And now we can have just have a special final case, have maybe 1 thread only, just compare these two. I could have done a bigger example actually, but it would take a long time to make this video. But this is sort of the idea. So what would happen, just to recap, if you had 16 threads, it'd be 16 partial results here. You would spawn 8 threads, and then you have 8 teams make it to the next round. Then you would spawn 4 threads. Then you would spawn 2 threads. Then spawn 1 thread, and then you have your final sort of 2 champions left, your Super Bowl, and you would compare those two. So same idea here. You have these 2 now, and then the winner of these 2 is the true smallest value. And once you finally have that, so now you're going to have only 1 element in this vector over here at the very end. Just 1 element all by itself. We'll say A13, sort of wins. That was the smallest one. So now what we're going to do is take the value at index 13 in my array and swap it to the first element of my initial array. And that's going to give us sort of the first step of selection sort. Guess what happens now? Now you have to do the same process, but now on a smaller list. And you have to sort of divide it up the same way, but now you have less elements, so potentially 1 thread might do less work, because say you have only 14 elements now. If I divide it by 5, well, we're going to have a little left. We're not going to have a perfect division. So what's going to happen is each thread will take 3 elements, and then the last thread would take, I would think it would just take, hold on, let me see, so make sure I don't mess this up here. So if you have 14, you have 5, 10, like that. So the last thread, would do only 4 elements. Yes, the last one would do a little bit less work, but it's okay though. And then we do the same exact thing again. So all we're doing is we first have our first phase. We just do this, we break it down to small pieces like this, have each thread do a linear search, a linear traversal to find that min element. We push each result onto this partial, onto our tournament vector. And then we spawn half the threads initially to simulate. You only compare adjacent elements. So think about it. If you have, let's say, 16 elements, you want to have between two threads, we can just do 8 for each one. So this was not a good example, but it might have been a good example because some elements, sometimes you may not have a perfect square of elements. You may have some weird thing like this. So actually, this wasn't a bad example. But then you run this tournament algorithm here, so you always compare adjacent elements. One winner moves on. You keep doing this until eventually you have only one element by itself like that. And you're going to spawn always half as many threads each time. So let's say, just to recap it again, if you had 16 elements, we spawn 8 threads, and then we're going to have 8 elements left over. We spawn 4 threads for that. Then we would have 2 threads left, and then so forth, until we have one element all by itself, and that's going to be when we're done. So then we kind of put it to the next smallest element, and we keep doing this until we finally hit the end. Now, for this algorithm as well, if you get to a certain point where we only have maybe just a few elements left over at the very end, you can just do a simple insert and sort now on that particular portion. So if, let's say, at the very end, let's say we can spawn 5 threads at most, or let's say we can spawn max threads amount at most. If there's only max threads divided by 2 amount of elements left over, then just do insert and sort. So for example, if I have, let's say, 5 threads, and there's only 2 elements left over, or 3 even, yeah, just do insert and sort. There's no point really doing this whole thing because you have such a small list now. Just go ahead and do it very simple. You can go ahead and even copy and paste insert and sort from the net. That's perfectly fine. I'm not going to really come after you for that because that's not really, I wouldn't consider that really cheating to do a little bit of that, but don't copy your friend's code with all of this. So anyway, that's basically the idea. So this would have been kind of a pain to write this whole thing up, but hopefully this helps you kind of see how to approach this problem. So other than that, I think I'm done with this video here. So if you have any questions, of course, you can always contact me on Discord and my graders as well. And other than that, I think I'm done. So take care, and I guess have fun sort of coding this.